right. Thank you guys for letting me know. I'm assuming you guys can see the screen all right too. If not, I'm pretty sure you guys would have told me by now. Before we begin, before we begin this seminar, I just want to congratulate all of you. You guys are almost at the end now. So in this seminar, as you guys will see, we're going to cover assignment number 9. And in assignment number 9, there are 2 questions that are worth marks. Now, in assignment number 10, which we're going to do next week, there is only 1 question that is worth marks. So if you guys are just concerned about your actual marks and no bonus marks, you guys are 3 questions away from being done this class, which is quite something. It went by really fast, so I hope you guys enjoyed it up until this point, and hopefully you guys keep enjoying it until the end. All right, so we're going to begin. Again, as I said in this seminar, we're going to be covering assignment number 9, which focuses on virtual work. Now, the assignment itself, it's actually 3 questions. However, only questions 1 and 2 are official questions, while question 3 is a nice bonus question. I know you guys love the bonus questions, so we threw back in a bonus question for your guys' benefit. Now, if we look at question number 1, it says, use the principle of virtual work to find the reactions for the following statically determinate structures. Assume a virtual horizontal displacement to the right, x star, a virtual upward displacement, y star, and a virtual counterclockwise rotation, theta star, about point A. So again, as you guys know in my seminar slides, very rarely do I include the images, but you guys have the images. The first one, of course, is a simply supported beam, and the second one is a cantilever beam. Now, if you guys look at this question, it says statically determinate structures. Well, we covered that in Eng 130, so of course you guys have the option to choose this question, but I don't recommend that at all, because when a virtual work appears on your final, you're going to need to know what exactly to do. So let's discuss the process of virtual work. The first thing that we have to do in these type of questions is figure out what is our virtual displacement. So let's say that we have a nice simply supported beam. It's just sitting there and we want to apply our virtual displacements. Now, luckily for us, the question gave us what our virtual displacements are. I'm not going to do it in the order of the questions, but the steps are all the same and you'll end up at the same spot. So one of the first ones I do is say, all right, well, it said that we had a virtual displacement upwards of y star. So I just take my beam, I move it upwards. As simple as that. And then it said, all right, well, we also have a lateral virtual displacement to the right of x star. So, all right, my beam has been moved up. Now I'm going to move it to the right. And then finally, we have a virtual counterclockwise rotation, theta star, about point A. So, of course, referring to my figure, the pin support, or that triangle, is obviously point A. And we're just rotating the beam counterclockwise about point A. Now, this is great because if we look at the original beam, which is shaded in gray, and the current position of the beam, virtual displacement, which is the purple beam, we can create a relationship of that vertical deflection. What is that relationship? Well, y star is equal to y1 star, so that just comes from the virtual upward displacement of y star, plus x1 multiplied by sine of theta star, and this comes from the rotation. And this is going to be essential to the principle of virtual work, as you guys are going to see. Anything that involves virtual work, we need virtual displacement. So the first step in this question, of course, find that virtual displacement. Well, now we have it. So once we have it, we can actually talk about what the principle of virtual work is, and it's actually very simple. The principle of virtual work states that the internal virtual work, which I deem as IVW, is equal to the external virtual work, which I deem as EVW. So as you guys have seen in the assignments here, also in the quizzes, everything in virtual work revolves around this principle. Usually in these type of questions, you guys will be asked one of 3 things. 1, find the internal virtual work. 2, find the external virtual work. Or 3, verify the principle of virtual work, which is basically finding the internal, finding the external, and making sure that they're all equal. Now, why is this important to us? Well, we have an equation. And equations, as you guys have seen, it's great for us because with an equation, we can solve for unknowns, and that's exactly what we're going to do in all 3 of these questions. So let's look at our particular scenario for question number 1 here. We have the external virtual work, which is equal to the internal virtual work, which is equal to 0. So you guys may be asking, well, how do we know that that internal virtual work is equal to 0, Clayton? Well, we have a nice formula for the internal virtual work of an Euler-Bernoulli beam, which is the case that we have in question number 1 here, where it's simply the integral over the length of the beam of EI multiplied by the second derivative of the deflection function multiplied by the second derivative of the virtual displacement function. Now, if we look at the actual deflection function, we don't really know that, so we can't really conclude too much from here. However, we do know what that virtual displacement function is. We solved for it on the previous slide, where it's y1 star plus x1 times sine of theta star. Now, if we take the second derivative of that bad boy, we're going to see that it's actually equal to 0. And if we take the integral of 0, well, we know this is actually going to be 0. So we're going to use this into our equation because now we know that the external virtual work, which is equal to the internal virtual work, is actually equal to 0. So the question becomes, all right, how exactly do we find that external virtual work? Well, quite simply, it's the summation of all forces multiplied by their virtual displacements. So let's say that I have a beam here, again, nice, simply supported beam with a point load right at the center there. We know that this load, once we apply it to the beam, is going to create some reaction forces at the supports of the beam. What we also know is that we have the virtual displacement profile of the beam, which we solved for before. So all we really need to do is take each one of these forces and multiply it by their virtual displacement. So if I'm saying, all right, well, if I'm trying to find that external virtual work, I'm going to look at my first force here, which is AX, and I'm going to multiply it by its virtual displacement, which we know is X star. So this is a lateral load. It has a lateral displacement. Not too bad. Now, if we move on to the next one, we see that we have a vertical load now, which is AY, and we multiply it by its virtual displacement. So the thing to keep in mind now is that virtual displacement in the Y direction, it changes over the length of the beam. So what I do is I say, all right, well, this is going to be the virtual displacement when X1 is equal to 0. Moving on, I can go to my next load P, which is going downwards, so therefore we go negative P multiplied by its virtual displacement. So this is going to be Y star at X1 is equal to L over 2. And then we move on to the last force, which is By multiplied by its virtual displacement, which is Y star when X1 is equal to L. Now this looks great, but we can make it more simpler. I guess that doesn't really make sense, but we can make it simpler in the fact that we know what that Y star function is. So what we can do is we can say our external virtual work is equal to everything expanded, and all I did is I took our expression for Y star and I substituted the corresponding X values. So for instance, if we're looking at AY there, we know that that occurs at Y star when X1 is equal to 0. Therefore, Y star in this case is simply just Y1 star. So nice and easy. We have a nice big long equation. Now we have to figure out what exactly we can do with this. So now that we have the external virtual work and the internal virtual work, we have a nice expression where we have all that external virtual work, which is equal to the internal virtual work, which of course is equal to 0. Now the question becomes, well, we have one equation, but we actually have three unknowns. We have AX, AY, as well as BY. So how exactly do we solve for three unknowns using one equation? Well, we're going to have to rearrange the equation. So all I did was expand each equation so that they're in terms of the virtual displacement. For instance, x1 star appears once with the term ax, so I have ax times x1 star. Now, if I look at y1 star, it appears 3 different times in my equation, so I'm factoring it all out. So I have ay minus p plus by all multiplied by y1 star, and then I did the exact same thing for that theta star. Now, the trick to the virtual work is this. The statement above must hold true for all values of x1 star, y1 star, and theta star. Therefore, everything in each one of those brackets must be equal to 0. How do we get this, Clayton? Well, let's say that x1 star and y1 star are equal to 0. Therefore, the thing in the last brackets there must be equal to 0, and you can do this over and over again. But what essentially happens is this. All of those things in the brackets, those must be equal to 0. Therefore, we have 3 different sets of brackets. Therefore, we have 3 different equations. Now we have 3 equations for 3 unknowns. Now, the best way to check if you guys are on track is if we look at each one of these expressions, it's exactly the same as if you were to do it in Eng 130. Looking at the first one, we have AX, of course, is equal to 0. Well, that's the same if we took the summation of the forces in the horizontal direction. If we look at the second expression where we got AY minus P plus BY, That's the exact same expression if we were to do sum of the forces is equal to 0 in the y direction. And finally, negative PL over 2 plus BY times L, that's exactly the expression we would get if we took the summation of the moments about point A. So that's a good way to make sure that you guys are on track. Compared to the actual static process of equilibrium, you guys should get the exact same answers. So that's question number 1. Doesn't seem too bad, or at least I hope it doesn't seem too bad to you guys. What do you guys think? Is there any questions concerning question number 1? Alrighty, I'm not getting a response yet. So again, if you guys want to ask at the end of the seminar, I'll be around. But for now, we'll move on to question number 2. And question number 2 is going to be a little bit more challenging than question number 1, but yeah, better than question 2 of the last assignment. But question number 2, it's not going to be too bad. So question 2 says the Cauchy stress distribution in the shown plate is given by, and as we can see, we have our nice 3x3 Cauchy stress tensor, and it says inside of the stress tensor we have x1 and x2, where x1 and x2 are coordinates inside of the plate with units of meters, and the plate dimensions are alpha is 6 meters, beta is 2 meters, and the thickness t is 1 meter. So that t right there, that's the thickness into the page. Now, what this question would like us to do is determine 3 different things. The first one is the equilibrium body forces vector applied to the plate. The second one is the traction forces on the boundary edges A, B, C, and D. And then finally, part C says, verify the principle of virtual work assuming a virtual displacement field U1 star is equal to 4x1. Now, if we look at this question, it's actually not too bad at all, because if we look at A and B, body forces vectors, well, we already know how to calculate that. That's not even really a virtual work topic. We covered that before. And if we look at part B, traction forces, well, we also covered that before. So that's really nothing new. The only thing really new to this question is going to be part C. However, the key to part C is knowing the external virtual work, as you guys may have guessed. And to calculate the external virtual work in these type of questions, we need both the equilibrium body forces as well as the traction forces. So, of course, A and B are going to be essential to part C. So let's go into it. The first part, equilibrium body forces, well, this isn't going to be a problem at all. You guys are experts, because recall that in static equilibrium, so the key here is static equilibrium, the following equations must be satisfied, where we have 3 equations, and each one of them is a function of basically 2 things. One is the stress tensor, and the other one is the body forces vector. So if we look at the first equation, everything in that red box, it's just the partial derivatives of our stress tensor. So we see we have partial sigma 1 with respect to x1, plus partial sigma 2 with respect to x2, plus partial sigma 3 with respect to x3. Now, all of those come directly from our stress tensor, which were given in the question, so that's not a problem. Everything in the red box, we know. If we look at the second component, which is in that purple box, that's rho B. That right there, that is our equilibrium body forces. That's what we need to solve for. But if we look here, we have 1 equation, 1 unknown. We can solve for rho B1, no problem. Moving on to the second equation, it's the exact same thing, where everything in that red box is simply the partial derivatives of our stress tensor, which we know. Rho B2, that's the unknown we want to solve for. We have 1 equation, 1 unknown. Again, that's not going to pose too much of a problem. Finally, the last one, the exact same thing, bunch of partial derivatives of our stress tensor, only 1 unknown, which is rho B3. We can solve for rho B3. So therefore, we have 3 equations. We have 3 unknowns. We can solve for all 3 of those unknowns, and those unknowns are rho B1, rho B2, rho B3. Once we know all 3, we know all 3 components of the equilibrium body forces vector. We just substitute it into the assignments, get those marks, and be on our way. So that's going to be part A. Again, should be nice and easy. We covered this in a previous topic. Not really has to do with virtual work too much thus far. Now, the second one, this is where things are going to get a little bit interesting, because we covered traction vectors, but this one has a bit of a trick in it. So let's recall the formula for a traction vector. We know that the traction vector is simply the stress tensor transposed, which isn't a problem because we know that stress tensor, that's no problem at all, multiplied by n, which is the normal vector. So the only question that's going to be a problem for you guys is, well, we're given the stress tensor, that's no problem, but what is that normal vector? Because we're not explicitly given the normal vector. What we are given is an illustration of our shape, and what we can do is we can use that to find our normal vector. So let's say that we had a nice square in the x1, x2 plane, and we wanted to calculate the normal vector for A. So of course the normal vector has a couple properties, and the first one is it points away from the surface and it is perpendicular to that surface. So if we look at our surface A here, we know our normal vector is going to look something like this, where NA is perpendicular to surface A as well as pointing away from surface A. So the second thing that we're going to have to keep in mind with these normal vectors is that they are normalized, which makes sense. Normal vector, normalized, so that's something that we're going to have to keep in mind. Therefore, if we were to look at normal vector A here, the correct answer would, in this case, be 1, 0, 0. It goes strictly in the x1 direction. It doesn't go in the x2 or x3 direction. Therefore, we know it's 1, 0, 0. If I were to enter 2, 0, 0, which has the same direction, but it's not normalized, you guys will get the wrong answer. So please make sure that is normalized when you guys go into these type of questions. So if I were to look at B right here, again, the same thing. If I wanted the normal vector for surface B, it's pointing away and perpendicular. So we know it's going to look something like this, which in this case would be 0, 1, 0. All right, so that's going to be the key here for the normal vectors. Once you guys have them, you guys are pretty much done. You have your traction vector, but there's one other thing that we have to consider, which is the location of the surface. So let's look at surface A here, and let's just say that surface A was located at a distance x1 is equal to 3. This is very important because if we look at surface A here, that x1 is equal to 3 is constant throughout the entire surface. Therefore, if we were to calculate the traction vector for A, we use the simple formula where we take the transpose of the stress tensor multiplied by the normal vector of A, but then we can substitute x1 is equal to 3 for all values of x1. Why is this? Because if we look at our surface here, we know that the entire surface is located at x1 is equal to 3. Now, quick little disclaimer, of course, your guys' assignment, that surface may not be at 3 meters, so please don't just use 3 meters because you saw it in the slides and carry on. That's not a good practice. Make sure you guys are doing these questions with respect to your own assignment. So this is how we calculate the traction forces. Not too bad again, and this is essentially part B. After we're done part B, we're going to get into the actual virtual work section, which is part C. And part C says basically verify the principle of virtual work. Clayton, what does that mean? Well, this just means that verify that the internal virtual work of the system is equal to the external virtual work of the system. So in order to do this, we're going to have to calculate both the internal virtual work as well as the external virtual work. And as you guys are going to see, it's not too bad at all. So we're going to start off with the internal virtual work because for a continuum, the internal virtual work can be found using a simple formula, which is the integral over the domain of the summation of sigma ij multiplied by epsilon ij star over, again, the domain. So if I'm looking at this, there's one thing that comes into my head. This is pretty gross. I don't really want to solve this yet. Again, there's a summation in there. I'm going to have to figure that out. I'm going to have to take an integral over a domain. I'm not sure what that means. So we got to try and simplify this as best we can. So the first thing I'm going to do is I'm going to tackle that integral. So right now it's the integral over the domain. What does that mean? We're basically integrating over the volume of this plate. So in this case, we have a plate. It doesn't matter if you have a plate or a cube or anything. We're basically integrating over the volume. So that single integral there over the domain can be exchanged for a triple integral. And what I'm doing is I'm integrating over all three of the x1, x2, and x3 directions. So if we look at the very left side of the integral, I go from 0 to t. Well, of course, that's that in-plane thickness, so that is the x3 direction. If I look at the middle integral, I'm going from 0 to beta. That's the height of the plate. Of course, this is with respect to the x2 direction. And finally, the innermost integral from 0 to alpha. This is over the length of the plate, which in this case is in the x1 direction. So even though this integral looks pretty scary, it's actually not too bad once you guys realize, oh, I'm just integrating over the volume. But if I were to take a step back, look at this equation from a whole, well, it's still pretty gross. And the reason why is we have a big summation in there of basically the stress tensor components multiplied by the virtual strain component. So in this case, I don't like i's and j's. I like it in terms of actual numbers. actual variables, which I can understand. So all I'm going to do is I'm going to expand out that summation to get the following formula. Now, if you guys are looking at this one, you guys say, Clayton, wait a second, this one looks more gross than the previous two up top. Well, it does look gross, but it's actually very nice. And the reason why, we know almost all of the components. So if we look at our three integration limits, t, beta, and alpha, well, we're given those in the question. Those are no problem at all. We look at the next big components. Those are the components of the stress tensor. Again, the stress tensor, we were given that in the question. Therefore, we know sigma 1, 1, sigma 2, 2, sigma 3, 3, etc., etc., etc. Therefore, the only thing that we do not know in this formula are the virtual strain components. So therefore, in order to solve this question, all we need to do is actually find the virtual strain components, epsilon star. So the question becomes, well, how do we determine these virtual strains? We know how to deal with regular strains, but what about virtual strains? Is there a difference? Well, there's actually not. We can calculate it the exact same way that we did before. You guys have calculated strains so many times. If we do it the exact same way that we did before, you guys are laughing. Nice and easy for you guys. Because since we have the virtual displacement functions, it's given to us in the question, we can find the virtual displacement gradient and then in turn the virtual small strain tensor. Again, the exact process that we had before. So if we look at our question, we had u star, and they gave us u1 star, which I have as 6x, x1, sorry, and then 0, 0. So from here we say, all right, well, I have my virtual displacement functions. I know that I have a nice formula to find the displacement gradient. Therefore, I can find my displacement gradient, where nabla u star is simply 6 in the 1, 1 position, and then the rest is 0. And I say, all right, well, I can take this a step further, because if I know that virtual displacement gradient, I have a nice formula for my strain tensor, or my virtual strain tensor. Therefore, I can find my virtual strain tensor epsilon star. Now, what's nice about this is, as you guys will see, you're going to have a lot of zeros in there. So that big long equation that we had in the previous slide, it should simplify quite nicely. And again, once you know what these virtual strains are, it's just a matter of substituting them into the equation and solving for your internal virtual work. So that's going to be the internal virtual work. It's not too bad once you realize that the process in determining virtual strains is exactly the same as if you were dealing with what I call regular strains, even though that's probably not the correct terminology whatsoever. So let's move on to the second part, which is the external virtual work. Now, as you guys will see with external virtual work, it's not usually dependent on just one thing. In a continuum, it's dependent on two things, that being the body forces as well as the traction vectors. If we were considering Euler-Bernoulli beams, it's dependent on the distributed load, the concentrated forces, as well as the concentrated moment. So it's usually not just dependent on one thing. So what we're going to do is we're going to go through the two components of the external virtual work in this question. The first one being the body forces. So if you want to calculate the external virtual work due to body forces vectors, we have, again, a nice crazy looking equation where it's the integral over the domain of the summation of rho bi multiplied by ui star. All right, so again, I'm looking at this thinking, integral over domain, not my cup of tea. Let's try and simplify it into integrals that I know, very defined integrals. And therefore, we can exchange it into the exact same thing where we had before, where we're integrating from 0 to t in the x3 direction, from 0 to beta in the x2 direction, and then from 0 to alpha in the x1 direction. Now again, I don't like summation, so we say, all right, well, can I make this a little bit simpler? Well, yes, you can, where we can take that summation and simplify it into the following, where we have rho b1 multiplied by u1 star plus rho b2 multiplied by u2 star plus rho b3 multiplied by u3 star. Now, if we look at this summation, it's actually the same as if we were to take the dot product between the body forces vector as well as the virtual displacement vector. So that's one way you guys could have done it, but this is nice and easy. Now, if we look at this one, it doesn't look too bad. Of course, my animation's a little bit off, but as we can see, we know all of those integration limits, so those aren't going to be a problem for us whatsoever. Moving on to, again, poor animation, we can see that we have three components of the body forces vector. Now, we weren't given these in the original question, but this was the goal of part A. So since we calculated part A already, we now have rho b1, rho b2, and rho b3. So the final thing that we need, of course, are our virtual displacements in all three directions. Well, again, these are something that we were given in the question. So if we look at the external virtual work due to the body forces vector, we know all of those variables. All we have to do is substitute it in, take the triple integral, we're good to go. So this shouldn't be a problem for you guys. Not too bad. But as we said, the external virtual work in this case is actually a function of two different things. The first one's the body forces vectors. The second one is the traction forces vectors. And this is probably a little bit harder than the last one because of the integration. And we're going to talk about that real quick. So if we were to look at the external virtual work of a single traction force vector. Now I'm highlighting this as single because we're only looking at a single traction force vector right now, but you guys have 4 traction force vectors. If you guys look at the question, we have 4 surfaces on our plate. Therefore, we need a traction vector for each surface. Therefore, we need to find the external virtual work of each traction vector on each surface. So what I'm going to do is I'm going to show you guys the process for just a single surface, and then you guys can apply it to the other 3 surfaces. It's actually the exact same process, so it's not going to be a problem at all. So if we were to look at the integral for the external virtual work of a traction vector on a surface, it's the integral over the partial domain of our traction vector dotted with our virtual displacement vector, again, over a surface. So the operation between our traction vector and not n, this should be our virtual displacement u star, is the dot product. So this is the first thing that I want to kind of emphasize into your guys' head. Tn dot u star, that's the dot product, and it's going to make sense because what's going to happen is we're going to have 2 vectors, but we're going to want to integrate. So of course, if we were to try and integrate 2 vectors, of course you can integrate a vector, but we've never integrated a vector in this course. So chances are, if you guys are trying to integrate a vector, something's probably a little bit wrong. Now, if we realize that if we're taking the dot product between 2 vectors, we're going to get one scalar equation, and therefore it's much easier to integrate. Now, if we look at those 2 components, we know what that traction vector is, we know what that virtual displacement vector is. The question really becomes in this equation, what am I integrating? Because again, this one isn't over the whole domain, it's over the partial domain. So what we're going to do is we're going to have a nice little figure again to try and figure out what exactly this is. So this is the same thing as before. I have a plate in the x1, x2 plane. I have a surface A with the traction vector A. So the key to this and figuring out our integration limits is realizing what domain that surface is in. In this case, our surface is in the x2, x3 plane. Therefore, if I want to take the external virtual work, I'm integrating over those 2 directions. Therefore, if I know it's in the x2 plane, I'm integrating over from 0 to beta, and since it's in the x3 plane, I'm integrating from 0 to t. And if I look at this, you guys may say, all right, well, we account for x2 and x3. How exactly do we account for the fact that it's at x1 is equal to alpha? Well, we just substitute. Every time we see an x1 in this equation, we substitute it as x1 is equal to alpha, because we know that at this particular surface here, x1 will always have a value of alpha. It'll always have a value of alpha, and that's why we can substitute it. And again, there's a little bit of a trick I like to use, is I like to say, all right, well, if my surface is in the x2, x3 plane, well, then I know that my integration with respect to should be dx2 and dx3. So that's kind of the way I like to remember it. After this, you guys will be good to go. Again, this is the external virtual work of a single traction force vector. You guys are going to have to repeat this for the other 3 surfaces, but once you guys do, you guys have the external virtual work, you guys have the internal virtual work, you have everything you need to solve for this question. So is there any questions concerning question number 2 at all? Or are you guys feeling pretty confident with it? It shouldn't be too bad. Shouldn't be. All right. Again, I'll be around after if you guys have questions. So that concludes the actual marked portion of this seminar. Let's move on to question number 3, which is the bonus question. So I know you guys love a good bonus question, and question number 3 is no exception. It is an absolutely great bonus question. It says, the shown beam below has a length L of 12 meters, Young's modulus E of 20 GPa, moments of inertia of I, which is equal to 1 over 250 meters to the 4th, and is subjected to a constant downward load of Q, which is 6 kilonewtons per meter. And it wants us to determine 4 different things. So before we go any further, I'm just going to say again, I don't have the illustration, but this is a simply supported beam. So I'm going to make that clear. It's a simply supported beam. Now, if we look at part A, it says it wants us to find the exact solution of the displacement equation. We're saying, all right, well, exact solution of a simply supported beam subjected to a distributed load. We've done that so many times. Part A is a piece of cake. So even though question 3 is a bonus, you guys should have nice, easy bonus marks just from part A alone. Now, where this question starts getting a little bit newer is parts B and C. Because part B says, find the approximate quadratic polynomial displacement solution using the principle of virtual work. And part C is the same thing, except instead of using a quadratic polynomial, it wants a quartic polynomial displacement solution, again, using the principle of virtual work. So this is very realistic of what happens in real life, because if we look at our exact solution, as you guys know, in order to find it, we solve a differential equation. Now, in this particular case, it's a very easy differential equation, therefore it's not a problem to solve. Real life though, yeah, right. Those differential equations are disgusting. They're not fun at all. So therefore, finding the exact displacement, it's pretty tricky. And if it's not tricky, it's very computationally expensive. So therefore, to save us time, money, as well as being able to actually obtain a solution, what we typically do is we approximate the solutions using the principle of virtual work or the Rayleigh-Ritz method. And as you guys are going to see, they're very, very similar. Finally, part D says, comment if the quadratic or quartic approximations match the exact solution. So again, this is going to be easy. Once we have our answers in part B and part C, we're going to just simply compare them to part A. Not too bad. So again, the real question here, or the real challenging part, is going to be part B and part C, and we're going to solve that together. So if we're looking at part A real quick before we jump into that, let's talk about the exact solution. I only have one slide because again, you guys are experts, where we can determine that exact solution by solving the following differential equation, where EI multiplied by the fourth derivative of the deflection function is equal to our distributed load Q. Luckily for us, we know what EI is, we know what Q is, therefore we can solve for this exact deflection function Y, and we need 4 boundary conditions. But again, we have a nice simply supported beam, therefore we know the displacement and the moment at each end of the beam, therefore we have our 4 boundary conditions. So part A, exact solution, should be a nice easy piece of cake for you guys. Where it starts to get challenging is the approximate solution. So this is something that's a little bit more complex, and why this is a bonus question, because as Dr. Sammer said, this is more of a graduate school topic. So if you guys get this, you guys can think really highly of yourselves. This is a complex topic, but I know you guys can do it because you guys are so incredibly smart. So again, as I was saying, although the differential equations in this course are simple, this is not the case in reality. Therefore, we can use virtual work to approximate the solution. The first step, though, is saying, all right, what is going to be our approximation polynomial? And this is where part B and part C are going to differ, but it's the only real part, or the only real section in which they do differ. So of course, in part B, we said that we want a quadratic polynomial approximation. Therefore, I'm going to say that my approximate solution is A0 plus A1x plus A2x squared. So the whole goal here would be saying, all right, what is A0, what is A1, and what is A2? For part C, however, it gets a little bit longer because instead of a polynomial, we want a quartic approximation. So therefore, we have the same terms as the quadratic, but then we add in an A3x3 plus an A4x4. So it gets a little bit more complicated, but not too bad. And again, the whole goal right now is saying, all right, how can I solve for all of those unknown A coefficients? So that's going to be the goal here. How can we use virtual work to determine what those unknown A coefficients are? Now, I'm going to show you guys the process on how to do this, but I want to make it very clear right now, when I show you guys this process, it's going to be for part B, which is that quadratic approximation. As you guys will see, depending on your level of approximation, the steps won't change, but they'll be a little bit more complex, if you will, and we'll describe how that happens. So for the next few slides, keep in mind that I'm referring to the quadratic approximation, not necessarily the quartic approximation. So the first step, once we have our approximation function, which in this case we said we're doing a nice quadratic one, is essential boundary conditions. You're saying, all right, well, hold on, Clayton. What? What is that? Well, essential boundary conditions are the boundary conditions that apply to displacement or rotation, not moment or shear. And you're saying, all right, Clayton, well, of course, boundary conditions help us solve for stuff. How can we use these? Well, these essential boundary conditions will actually help us solve for the unknown A coefficients right from the beginning. It won't help us solve for all of the unknown coefficients, but it'll help us solve for a lot of them, as you guys can see. So again, these correspond to displacement and rotation, not moment and shear. I know that a lot of you guys are saying, well, simply supported beam, we know the moment's zero on both ends. We don't care about that. We want displacement. So if we're looking at our simply supported beam, we have two displacement boundary conditions. We know, of course, at one end of the beam, when x1 is equal to 0, the displacement is going to be 0. Therefore, we can write out our approximation solution. Again, this is the quadratic one, not the quartic one. And we know it's going to be equal to 0. And from this, we can see very clearly that a naught is equal to 0. And this is great. If we look at our quadratic solution, what we had is we had three unknown a terms, a naught, a1, and a2, and we've already solved for one of them. We know a naught is equal to 0, therefore we only have two terms left to go. However, we actually have a second displacement boundary condition, which is that the displacement at the other side of the beam at x1 is equal to L, we know that that's also equal to 0. Therefore, we can say, all right, well, we can substitute everything in. And what I can do is I can get a nice expression for a1, where a1 is simply negative a2 multiplied by L. And just with that little amount of work, we've actually already solved for two of the unknown a coefficients. Therefore, if we were to proceed with the quadratic approximation, we only have one unknown left, which is a2. So this is why essential boundary conditions are nice. They allow us to solve for a lot of the coefficients almost immediately without actually having to get into virtual work. However, we have a2 left. Our boundary conditions are used up. Therefore, we're going to actually have to use virtual work. So let's talk about virtual displacement. So after implementing the essential boundary conditions, we can update our approximation equation with the solved coefficients. And you're saying, well, what exactly does that mean? Well, remember that originally our approximation solution was a naught plus a1x plus a2x squared, but now we know what a naught and a1 is. Therefore, we can substitute them into the equation, and now our new approximation solution becomes a2x multiplied by x minus L. So again, if we look at our new approximation solution, after the essential boundary conditions, our only unknown left, of course, is going to be a2, which is great. However, this is our approximation solution, and as you guys are going to see, we're also going to need a virtual displacement, which we call y star. Now, y star, you can basically have anything as y star, but the best way, or the most general way, is saying that our y star is actually the same expression as our approximation equation, with the only difference being our a coefficients. So if we look at our approximation solution, we have a2x multiplied by x minus L. Well, if I were to transform that into a virtual displacement, I have the exact same thing, but instead of a2, I change that to a2 star. All right, so that's going to be the key here when solving for this virtual displacement. All we're doing is we're taking our current approximation and we're switching all of the a coefficients with the same a coefficient, but with the star. So we're making it basically virtual. Now, this is again for the quadratic, but I want to make a quick note here. When you guys are solving for the quartic solution, you guys won't just have a2, you guys will have a3 and a4. So make sure that you guys swap a3 and a4 as well in your quartic solution. So that's going to be a little bit of a hint for you guys. Why is this great? Well, let's talk about internal virtual work. So to solve the remaining coefficients, as I said, we're going to utilize the principal virtual work, which is the internal virtual work is equal to the external virtual work. And since we have a nice Euler-Bernoulli beam, we can actually calculate that internal virtual work as the integral over the length of the beam of EI multiplied by the second derivative of the approximate displacement function multiplied by the second derivative of the virtual displacement function. So although this looks a little bit crazy, let's look over the parameters. First, we have EI and L. Well, we know both of those. Those are constants. They're given in the question. Those are no problem at all. But how about the two displacements? If we look up at the first one, our approximate displacement function, well, we know that. We defined that on the last slide. If we look at our virtual displacement function, y star, again, we defined that on the last slide. So if we actually look at this integral, we know everything inside of there. Therefore, all we have to do is substitute everything in, and we're going to solve for that virtual work. So that's nice and easy. That shouldn't be a problem at all. How about the external virtual work? Well, for an Euler-Bernoulli beam, we have a nice equation for the external virtual work, which is this, which is basically we're taking the integral over the length of the beam of the distributed load multiplied by the virtual displacement plus the summation of any concentrated forces or moments multiplied by their corresponding virtual displacements or virtual rotations. Now, even though this looks pretty crazy, our scenario is actually pretty nice because the only loading or external loading that we have on this system is a distributed load. Therefore, we have no concentrated loads or no concentrated moments. What does this mean? Well, it means that those two summation terms cancel, which is great because now our external virtual work is simply the integral over the length of the beam of our distributed load Q multiplied by our virtual displacement Y star, which is great because we know both what Q and Y star is. Therefore, we have our external virtual work basically solved. All we have to do is substitute it into the equation, solve for it, we're good to go. All right, so that's both the internal virtual work and the external virtual work. But what can we do now that we know both of them? Well, we're going to solve for that unknown A coefficient. So of course, using the principle of virtual work, we know that the internal virtual work is equal to the external virtual work. And again, at this point, we know what both of those are. And what you guys will find is you guys are going to have something, something, something times A2 star is going to equal to something, something, something times A2 star. Well, if I have A2 star on both sides, of course, A2 star is going to cancel. Therefore, I'm going to have something, something, something is equal to something, something, something. And the only unknown in there will actually be A2. Therefore, we can actually solve for what A2 is. And once we know what A2 is, we both know what A0 is, A1 as well as A2. All we have to do is substitute our coefficients into our original approximation equation, and we have our approximate solution. So again, that's all we have to do. And this is what's nice about external virtual work. We have an equation, we have an unknown, we're able to solve for that unknown. So again, this is going to be for the quadratic. It's going to be fairly straightforward, as you guys will see. Now, this is where I typically end things, but I want to make a very specific note because I know we'd get a lot of emails if we don't. So let's talk about the quartic solution. So up until this point, all the steps are the exact same. The only difference with the quartic solution is you're going to have A2, A3, and A4. Now, when we get to this step here, after we calculate the internal virtual work and the external virtual work of the quartic approximation, what you guys are going to see is it's going to look something like this, where we have something, something, something times A2 star plus something, something, something times A3 star plus something, something, something times A4 star is equal to, and basically the same thing on the other side. Now this looks like a problem because we have one equation with three unknowns. Those unknowns are going to be A2, A3, and A4. So remember back when we talked about question number 1, we said that the principle of virtual work has to be valid for any choice of A star. Therefore, we can solve for each value of A star independently. Clayton, what exactly does this mean? Well, let's look at the equation above and let's just say A3 star and A4 star equal to 0. Well, that simplifies my equation into the following, where I have something, something, something times A2 star is equal to something, something, something times A2 star. Now, if we look at this time, it's exactly the same as the quadratic, where A2 stars will cancel and we create an equation. Now, you guys are going to say, an equation? What do you mean? I thought we were going to solve for A2. Well, as you guys will see, that something, something, something inside of the A2 star, that's going to be a function of A2, A3, and A4. So again, even after the A2 stars cancel, we can't solve for anything just yet. However, if we repeat this process with A3 star and A4 star, what we get is two more equations. And at this point, we'll have three equations. We'll have three unknowns, those unknowns being A2, A3, and A4. Therefore, we can solve for all of the unknown coefficients, and life is good because we then have the approximation. So that's how you guys do the bonus question. It should not be too bad. And I'm going to say should not be because you never know. I always get things that amaze me. But yeah, that's it, guys. So is there any questions concerning the bonus question?